Welcome to Part 2 of Chapter 7, Human Health and Environmental Toxicology. We were last talking about endocrine disruptors, so take a few minutes and glance back at those notes. We were talking about those. Endocrine disruptors are things that change the hormonal balance in your body. And when they change the hormonal balance, one hormone affects another hormone's production, and we spoke about in birds how it decreased the shell on the eggs, and so the bird eggs were more vulnerable. We also talked about how it affected the male alligators to where they would not mate. Another example of this is that researchers have found in the Platte River just south of Denver, that male fish are actually taking on female characteristics, and therefore they're not reproducing. So, and that is because of birth control that is urinated out of the female system, and then wastewater being emitted, clean water, but water that the chemicals have not been taken out of, and so it's very high, causing increased estrogen in these fish. So now we're going to look at it. How does this affect humans? Well, it can cause infertility. It causes hormonally related cancers. So hormonal cancers can be breast cancer, testicular cancer, thyroid cancer as well. And your thyroid regulates your metabolism, how you grow and develop, and how you use the food that's put in you. Basically, is your metabolism. And there are 3 or 4 different hormones that regulate that system. So that can be an issue with endocrine disruptors. Phthalates have been implicated as endocrine disruptors. This is a category of chemicals you find in cosmetics, fragrances, nail polish, medication, toys, and food packaging. So we're exposed to these toxins really on a daily basis. Maybe girls more than guys, because we're putting on cosmetics and smelling good and pretty nails and that kind of thing. We need to be aware that chemicals have to be presented into your body at a level that causes this. There are levels of the chemical that you can be exposed to, and it does not build up enough in your body to cause problems. So you are exposed to those, but everybody's a little bit different in how they process it and what levels are actually going to cause abnormalities in the body. So none of these by it themselves is an issue. The levels are extremely low, and they should not affect you in a bad way. The thing is, you never know if you're applying makeup, you're getting your nails done, and you're also wearing perfume. How do those combine? And the combination of those 3, does it put you over that level? So those are the things that we have to be cognizant of as we're using chemicals in our everyday life. Determining health effects of pollutants, as I was just talking about. We look at it from toxicology is the study, and a toxicant is the chemical that we're testing and will have adverse health effects. We look at it based on how much you're getting and the response to that amount. So it's called dose and response, and those are the definitions you can pick up. 2 types of toxicity, one is acute and one is chronic. Acute means that you have a high enough exposure immediately to cause immediate onset of symptoms. This is Say you were at Chernobyl when it melted down and nuclear radiation got loose, and you were in the vicinity of that, you would show acute radiation poisoning, followed by death, if you were close enough. You would get very, very ill, very, very quickly, and then result would be death. Chronic toxicity could be from radiation poisoning, where you're not getting that huge dose up front, but you're getting a small dose continually. And over time, then that small dose, as you age, could cause one of the big things with radiation poisoning is thyroid cancer. So that could cause thyroid cancer. Also causes other soft tissue cancers as well. So that would be a chronic toxicity. Smoking is a chronic, if you will, toxicity. The chemicals that you inhale in a cigarette over time wear your lungs out and cause cancer. So that would be a chronic toxicity. Toxicity, there's two measurements. There's an LD50 and an ED50. LD50 is a lethal dose. What that means is when we run a test of organisms, maybe it's mice or whatever have you in the lab, we look at the dose or the amount per kilogram of body weight that kills 50% of the test subjects. Obviously, that's not a dose we want to get to. So that's a bad dose. We'll look at some of these common chemicals. Caffeine, 200 milligrams per kilogram of body weight. Lead, 20 milligrams, not very much. And nicotine, 2 milligrams per kilogram of body weight, and this has been tested on rats. So we usually test on rats. They respond very similar to the way a human responds. That's why we use them in these tests. And we extrapolate data. And we can do that because I want you to look. LD50 means lethal dose to 50% of the test population. In milligrams of the chemical per kilogram of body weight. Per kilogram of body weight. The ED50 is different. Lethal dose, dead. ED50 is effective dose. Effective dose. Now, think about effective. I know when I think about effective, I think, oh, well, that's a good thing. But not in this case. It is a negative. So think negative. Effective dose means that 50% of the population is starting to exhibit symptoms to whatever toxicant it is. Doesn't mean they're dying, but you're seeing abnormal behavior, abnormal respiration rate, abnormal neurologic activity, something like that. And if we have 100 rats, 50% of them are showing symptoms. Doesn't mean they're dying, but at that dose, if 50% of the population is showing symptoms, we don't want to be there. We certainly don't want to be at the LD50, but we've got to even go lower than the dose they're getting at the ED50. So we're going to be looking at a dose response curve, and that shows when the rats get to their ED50, when they get to their LD50, and it also shows a threshold level, and that's the maximum dose with no measurable effects. So that means none. So basically that's the lowest or highest dose without not one of the rats showing any response. That's considered the safe dose. So here are our graphs. We're looking at, in the first graph, ED50, here's our threshold. we're looking at, and it doesn't matter what the dose is, we're going from a very low dose to a higher dose, and what we're looking at here is milligrams per kilogram of body weight and percent of population showing response. So we're looking at being symptomatic. So as we go along here, we've given one dose, we give a higher dose and a higher dose, and this is the threshold level. Notice that not one of the rats has shown any response, but when we go to this next dose, we're starting to see some response in rats. Then we go to the next dose and a higher response, and which is about probably 17%. Then this is where we have 50% and we drop down, and this is our ED50. This is the dose that 50% of the rats are showing response, whatever the symptom is. Might be throwing up, neurologic problems, we don't know, because we don't know what this is. But 50% of the individuals are showing that. Now, this is really important. You will get these graphs, and they will be tested. And you need to understand that this means effective dose. So this is where you need to show effective dose. This is not the effective dose. If you pinpoint here, this is 50%. This is the effective dose down here, because I want to know how many milligrams per kilogram. And so that is over there. Now, let's look at these two. You have two toxicants, A and B. A is blue, B is red. And we have two different ED50s. So which one, this is a hard one, which one is more toxic? A or B? Why? A is more toxic because it has an ED50 at a lower dose. We don't know what these doses are, but this is a lower dose than for B. Now, I might say which one is more toxic or is more symptomatic at 25%. So then we go to 25%, and the first line we hit is B. Drop it down. Why does my cursor keep leaving me? Drop it down, and there's the dose right there. So keep your finger on that one. 25%, let's go to B. And B, we're going to be right here. So at 25%, that means 25% of the individuals are showing response, then that's going to be B. But as the dosage gets larger, then toxicant A shows more of a response more quickly. But B before we get to 25%. So think about that. Look at that graph. Children and chemicals are a little more intricate and more cause for concern than adults. Number one, children's bodies are still growing. Their brain has not completely developed. As children are growing, they weigh less than adults. So when we look at milligram per kilogram and their total body mass in kilograms, they can handle less because they weigh less. But another thing, and is it in your slide here? No, this isn't in your slide, so you need to put this down. Children breathe faster than adults. Put your biology hats on. If children respire faster than adults, they're bringing more chemical in at a higher rate. They have to breathe faster than adults because they need more energy. So they're creating more ATP because they're growing. They're not just metabolizing their food. They're actually growing. So they need that. Therefore, if I was to breathe for 10 minutes and a child of 6 or 7 were to breathe for 6 minutes, the same air, and it was full of pollutant, that child would have more pollutant in his little body than I would in mine after 6 minutes. Not only is the child smaller than I am, but the child is also still developing and now has more total amount of pollutant in their lungs than I do. So that is not good. So also, kids are more susceptible to chemicals because they play on the floor, they play on the lawns. They don't necessarily wash their hands like older people do. When I get dirty, I wash my hands before I go pick up food. Kids don't think that way necessarily, and definitely you should. Let's look at this picture. These are basically 4-year-old girls, and this is in your book too. One set of girls were not exposed to a pesticide. The other set were exposed to pesticide on a daily basis. These are their neurologic abilities displayed here. They were told to draw a person. And the ones not introduced to the pesticide, excuse me, you can see they could draw a person, what they saw. Now, the little girls that were susceptible to the pesticide, and both of these groups have had the same educational background. They've been exposed educationally to the same things. So, the pesticide is the only difference, as close as you can get with humans. So, the pesticide, the ones exposed to that pesticide were told to draw an image of themselves, or a person. And this is what they came up with. So, their neurologic capacity has been inhibited. Now, can we take them away from that environment? And will they start to develop? Will this clear out of their systems? Maybe, maybe not. And that's the thing. If abnormalities are caught early and the toxicant is removed from the person, or the person removed from the toxicant, some of them will go ahead and develop. Will it be delayed for a few years? Yes. Could they have permanent delay of brain activity? Yes. Depending on the toxicant. Some might heal, some will not. How do you identify cancer-causing substances? Well, that's what a toxicologist does. We have two people, toxicologist and epidemiologist. The toxicologist works with the doses. They're the ones that do the ED50s and the LD50s. And the epidemiologist looks at exposure groups. So they're actually doing the social study. And then they work together to develop how and if that toxicant really is a carcinogen, endocrine disruptor, or something bad that goes on in society that people should not be exposed to. Problem is that when we look at toxicants, we look at them in any scientific research. You have to look at one thing at a time. You can only have one variable. So you're not exposed to just one toxicant. But when we were talking about the fragrances and the nail polish and the 5 phthalates, you're exposed to several. So how do those work in your body? And do they each cause issues? Do they add up and cause a worse problem? Sometimes they can be antagonistic, and they can actually lower the effect. So that, I guess that would be a good thing. But it's hard. This is why it's hard to determine if one chemical is a carcinogen, if one chemical is truly an endocrine disruptor. That's the end. Oops, this is the end of section 2. And we will do part 3 in class.